Log on, tune in, find out. Another good idea from Cambridge.
Okay, thank you. So today I'll talk about G-Higgs bundles and Hitchin-Kobayashi correspondence. Okay, so let me just remind you what we did last time. So we had our surface, or group G, the maximal compact H. Say, think about maybe general linear group, or SLNC, or SLNA, or the symplectic group. Some examples to keep in mind. So we have this decomposition of the Lie algebra and this isotropy representation, iota. This was just taking the adjoint action of G on the Lie algebra and restricting to H, and see that it preserves this decomposition. And let's just fix now the principal H bundle. And we saw that we could identify the character variety for representations of the surface group by 1 sigma G. And let's fix also the topological class. We saw that that could be identified with the space of solutions, a theta to a certain set of equations. These equations divided out by automorphism, the gauge group of automorphisms of EH. I call this the following Simpson, the Betti moduli space, MD sigma G. So D here was the topological class of the bundle, given by an element of the fundamental group of G, or H if you want. Okay. So the correspondence was that first we identified this with the flat G connections on the corresponding principal G bundle to this. And we found a harmonic metric in the G bundle. And we can get over to these solutions on the fixed EH bundle by just pulling back the solution we had on that reduction to EH. Okay, so what's important to notice here is that this depended on the choice of conformal structure on sigma. So a conformal equivalence class of Riemannian matrix on sigma, okay? And that, if we have such a conformal structure, we know we can measure angles, so we can in particular multiply, or we can rotate by 90 degrees, so that means we can multiply by I. So this really means that we can make our surface sigma into a Riemann surface. We have an almost complex structure, and since we are in complex dimension 1, this is integral. So this becomes a Riemann surface. So this conformal structure so the plan is now to use this Riemann surface structure to get from this differential geometric world into the world of algebraic or holomorphic geometry, and then sort of complete the correspondence between surface group representations and G Higgs bundles, okay? Right, so first step, we want a holomorphic bundle. So we started out by this H bundle, so I can get a complex principal HC bundle I can get that just by extension of structure group, and but that's for now just complex. So in order to make it into a holomorphic bundle, we take the holomorphic structure defined by this connection A. So given an A, we get a holomorphic principal H bundle, holomorphic structure induced by A, and to that we have associated a covariant derivative. So whenever I have some associated vector bundle to EH, but that's not quite what I wanted to say. What I want to say is, well, this is not the holomorphic bundle yet, so let's take some associated vector bundles. So V is some HC representation. Then we have an associated, for now, just vector bundle. And we can, to A, associate a covariant derivative. So let's call that D of A. And that we can split into its 1, 0, and 0, 1 paths. So let's say dA and D bar A. And then the holomorphic sections of EA are just the ones that are killed by this D operator. So the smooth sections that are annihilated by D bar A. So H naught X H V is the kernel of D bar A. Okay. So it gave us that gave us a holomorphic principal HC bundle. So that's sort of half of our data. We got something holomorphic out of A. Let's now try to get something holomorphic out of theta. So let's complexify. So let me take GC, the complexification of the Lie algebra of G. Out of this data, we have a compact real structure. This is actually just the, call it top tilde. So this is an involution. It's a compact real structure, which we can get out of the compact, maximal compact H and the Cartan involution on GC. So this is a compact real structure. So for instance, if we on the GLNC, this is just taking a matrix to its conjugate minus its conjugate transpose. Okay, and now let me use that to define an operation on one forms on X, E, H, and C. So I'll take here this GC here. Also, we have a corresponding Cartan decomposition, so we just complexify everything in sight, and of course the H still acts by the isotropy representation on MC. So we have this associated bundle, and we can get some sort of real structure here. Let me call it. Let me call that then tau from this space to itself. So tau. So something in here locally can be written as a one form alpha times some A in M, and what we're doing, we're just using that compact real structure on the matrix pad and taking the conjugate of the form. Okay, so that now makes sense because we are on a Riemann surface. Okay, and we use that then to write our theta, just as we could decompose a connection or a covariant derivative in 1, 0, and 0, 1 parts. We can do something similar with theta, and what comes out is that we write this as something that is called phi minus tau phi, where now phi is going through the 1, 0 part of theta, and tau phi is the 0, 1, minus tau phi is the 0, 1 part. So it's E. Let's put it like this. Okay, so this is not yet holomorphic. Okay, this is a smooth 1, 0 form with values in this bundle. Okay, since we have our holomorphic principal bundle structure there, we can of course ask whether it's holomorphic, and it's holomorphic exactly when d bar A of phi is 0. Okay, and then we have a very nice observation. So if we translate these equations here, let me call them star. If we translate them into these terms here using phi instead of theta, one sees that they're equivalent to these famous Hitchins equations. So the two last equations there actually are equivalent to this one, which means that phi is really a holomorphic object if we start with a solution to these equations. Okay, so now we have our holomorphic object consisting of a principal HC bundle and this holomorphic phi, and that object is exactly what is called a G Higgs bundle. So let's write down the definition formally. G Higgs bundle on X is a pair. Let me just write it as E phi. Okay, because now we no longer need this to be an H bundle, but just an HC bundle, where E is a principal holomorphic HC bundle, and phi is a holomorphic section of this EMC, so this associated bundle, and this, remember, it was a 1-0 form, so actually we should twist by the holomorphic cotangent bundle here, which is the same as the canonical bundle of X. Canonical bundle. Okay. All right, so let's just look at this for a second. Maybe it's instructive even to think of the case where H is just equal to G. Then Hitchin's equations there just say that A is a flat. Well, if we're looking at the simplest possible case where where G is just a unitary group, then the first equation just says that A is a flat unitary connection. Phi doesn't exist because M is 0. So then all we did was out of a flat unitary connection to produce a holomorphic vector bundle. Okay? And then, of course, we have the Narasimhan-Seshati theorem, which says that that vector bundle is actually going to be stable, or at least polystable. And in the other direction, if a vector bundle actually is stable, then it admits a metric such that the associated Chern connection is flat. Here we should stay in the degree 0 case, of course, for this. Okay. Yes?
So this term is the involution defining a maximal compact form in GC compatible with the real structure.
That's right, yes. So this is exactly equal to sigma composed with theta. Let me put it a capital theta. So this was the Cartan involution, and this sigma here is the real structure on GC. So sigma. So that's real structure defining G, and this one is the theta. So you'd expect maybe to have some sort of stability condition that is satisfied for G Higgs bundles that come from solutions to these equations, and conversely that stability condition allows you to solve the equations. And indeed that is the case. So that's the Hitchin-Kobayashi correspondence. So also there are semi-poly stability. Okay, so this in this general setup is it's a fairly involved, complicated notion. So in fact, it can be seen as a particular case of the stability condition for principal pairs that was studied by Radlow, Garcia Prada. And Munded. And there is a general Hitchin-Kobayashi correspondence for this setup. So I won't go into details about the general way the stability condition looks. You may remember already from Thomas Gomes' lecture that for principal bundles for principal bundles already without any kind of associated section, the general stability condition looked rather complicated, and this, in a sense, is quite similar to that condition that he showed us. So let me just mention one or two features of this. So actually, there is, in all generality, there's a parameter alpha in the story. However, for us, in this G Higgs bundle case, you could consider it, but in fact, if you're just interested in getting the correspondence back to representations of the fundamental group, one should take the value alpha equal to 0. It folds out again, so I won't go into that. As I just said, the stability condition is formulated in terms of reductions to parabolic subgroups, say P inside HC. Then you have to look at also antidominant characters and so on, and slightly involved story. So I'll just rather in some examples tell you a little bit more about what it says than try to go into the general condition. Okay. Right, so stability conditions, as we learned, are good for Hitchin-Kobayashi correspondences, but they're also good for constructing moduli spaces, as we have been explained already. And turns out that this is also the right, at least in cases of interest, let's say. It's the right condition for doing a GIT construction of moduli spaces. So I may say too much, which, so let's say we have here Schmidt's general construction of moduli for decorated bundle gives us certainly gives us a moduli space of G Higgs bundles of fixed topological invariant D, which we call the Dolbeault moduli space. Not totally, at least in the cases I wrote up there. There is there may in general be some. It's not totally clear that this stability condition is actually the same as Schmidt's stability condition in all cases you can think about, but it's not clear that it's not the same either. But okay, that already wrote. Yeah, let me just say that this moduli space here. So. So of course, as usual, this parameterizes S-equivalence classes of semistable G Higgs bundles, or we can interpret that as isomorphism classes of polystable guys. All right. Sorry? See it?
You made some statement about it's true for some G, but not other ones. Maybe, what was the actual statement about it?
The statement is that, let's say, at least for those G's I wrote up over there. So it's certainly true for more G's. Okay, so I guess I will. But let's see. Okay, so I could write a long list of G's for which I know it's okay, okay? And I can't write a list of any G for which I know that it's not okay. Okay, so, all right, so let me just put up then the theorem that I already alluded to, the Hitchin-Kobayashi correspondence. So I think here the names to information are Hitchin and Simpson, and okay, so for the generality needed for this G Higgs setup, these names here also, and maybe myself. So the theorem says that E phi is polystable if and only if there exists a reduction to some EH inside E, where this is a H bundle. So again, I'm denoting the reduction to H by some small h. Such that the A phi, the pair A phi, what we get out of the reduction. So phi is of course just phi, but A is then the Chern connection associated, given by A. So the unique compatible H connection that induces the right holomorphic structure in E. If and only if this pair satisfies the Hitchin equation. Equations. Okay. Moreover, this gives bijection. That's A phi pairs A phi satisfying Hitchin's equations modulo H gauge equivalence with the moduli space of G Higgs bundles. So this last statement is slightly stronger than just the statement about the solution, because it says that really isomorphism classes of G Higgs bundles correspond to gauge equivalent classes of solutions. Okay, so here, of course, to make sense of this, we should be working on a fixed EH. So to get a solution, so out of some reduction to some EH bundle, to get a solution on this fixed EH, just take some isomorphism, which you can always find from EH to EH, and pull back some solution by this F. Okay, so the theorem here gives you a solution, A tilde phi tilde, on this EH, and you just pull it back via some isomorphism. And that's how you make that correspond. All right. So what was just on this board, which I just erased, was, of course, that this space here was identified with the character variety. So altogether, thank you.
Sort of a stupid question. The second part, I mean, the first part, you only say there's some reduction of structure.
Mm-hmm.
The second part, you make it sound like if that's true, then there must be only one.
Yeah, exactly. So there's the second part has more information. It includes a uniqueness statement, right?
And is there really more information? Was I supposed to already see that?
No, that is extra information. Yeah. That is certainly extra information, but which is part of the theorem. So this can be interpreted as some sort of symplectic reduction theorem. Okay, so you can think of this general Kempfness picture of you have a Kähler manifold, you have an action of some compact group that extends to a complex action, so you can, and then you can have a moment map and so on, and you can see that the symplectic reduction is equal to the whatever the GIT quotient or something like this. So you're saying that every GC orbit contains, every GC orbit intersects the zero set of the moment map, okay? And the intersection is unique up to the G action, to the compact action. So the uniqueness statement is also important to get the identification of the moduli spaces. Okay, so the upshot is then that the character variety can be identified. So I'm a little bit loose here with the moduli space of G Higgs bundles. X G. So I've changed the name of sigma to X. I hope that's okay with you, because of course as a surface it's just the same. And it's worthwhile pointing out that this, in general, I think the best you can say is that this is a homeomorphism, just because we didn't really give much structure to this in general, just that of a topological space, okay? But even if, for instance, G is a complex group, this is a certain, if G is GLNC, for instance, this is actually a variety, complex variety, but the complex structures are not the same, okay? Because they come from different places, you see. Over here, the fact this is a moduli space of algebraic or holomorphic object on this Riemann surface, okay? So the complex structure here depends on which Riemann surface structure you have on X, whereas here there was no, you should just put this sigma here, okay? So it's worthwhile making that point. So you have, if G is complex, you have two different complex structures floating around here. And this is actually what gives you then the hyperkähler structure on the moduli space. Okay. All right, let's see some examples of this. So let's take, for instance, GLNC, or maybe SLNC, almost the same thing. So what is a G Higgs bundle? It's just a rank n vector bundle and a Higgs field, which is exactly what Norbert Hoffmann was just telling us about. So phi is a holomorphic section of and V tensor canonical bundle. In case we are in SLNC, we should fix the determinant bundle to be the trivial one, and phi should have trace 0. Stability is the usual stability for usual Higgs bundle, so it just says that the slope of, say, W is, let me write semi-stability, less than or equal to the slope of V for any sub W which defines a sub-Higgs bundle, so phi of W has to be inside W, tensor canonical. Okay. So let me. It's a very so if we take n equal to 1, then a Higgs bundle is just a line bundle and an endomorphism valued one form, but the endomorphism of a line bundle is just a trivial bundle, so actually all we have is some L phi, where phi is a one form. So what does our identification here say? So the character variety, since the group is abelian, this quotient by conjugation of G doesn't do anything, so actually the left-hand side is just the complex characters of the fundamental group. And what's the right-hand side? Well, so this moduli space of pairs of this kind, line bundle, one form. So of course, this is dual to by Sayre duality. This is in fact just dual to H1XO, which is just the tangent space to the Jacobian at the point L. So this is really just the cotangent space to the Jacobian, the cotangent bundle, sorry, to the Jacobian of X. Okay. And if we look at the infinitesimal version what we have here is just the first cohomology of X with coefficients in C, and so here what we're getting is just H1 X O X plus the Higgs field which lives here in H0 X. Okay, so this is of course H10, this is H01. So we're just getting the Hodge decomposition for, in fact, we're just getting the Hodge decomposition for the usual first cohomology. Okay, so that's why this is sometimes called non-abelian Hodge theorem. This is Simpson's terminology, Hodge theorem. Okay. So it's a fun exercise to work this out from this sort of Higgs bundle point of view. If you are interested in learning more about rank 1 Higgs bundle, there's a nice paper in the memoirs of the AMS by Goldman and Shear. Okay. So move on to another example. So for instance, if our group is, say, maybe SLNR, I'm not taking GLNR because I want to avoid complications coming from non-connected groups. Then what is a G-Higgs bundle? Okay, so the maximal compact here is just the orthogonal group, so we'd have to take the complexification to get the structure group of the principal bundle. So that's ONC, so that's an orthogonal bundle. Certainly SON, thank you. So that's a special orthogonal bundle. Let me call that V. So we can think of that as a rank n vector bundle with a quadratic form, non-degenerate quadratic form, and a Higgs field phi. So where does phi live? So it lives in the isotropy representation. So these are the skew symmetric matrices. So phi is symmetric with respect to this quadratic form. So phi H naught X. Symmetric, let me write it like this. Symmetric endomorphisms with respect to the quadratic form of V, and we should take the trace of phi. Trace of phi equal to 0, just because we've fixed the determinant. Okay, so C is an SONC. Okay. Okay, I'm not going to say much more about that. I'll move on to another one, which is, in a way, both interesting and quite a paradigmatic example, which is the real symplectic group. So the maximal compact here is UN. The complexification is GLN C, so this is our H. C is GLN-C, and the isotropy representation here in terms of the standard representation of GLN-C is the second symmetric product, direct sum with its dual. Okay, so this Cn is the standard representation of GLN-C, and I should have put a dual here. Okay, so what is a G-Higgs bundle then? So we have to have the GLN-C bundle, which is just an ordinary rank. We can think of that as an ordinary rank n vector bundle, V. And then we have a Higgs field phi. And where does phi live? It lives in this bundle associated to the isotropy representation, which is then S2V, direct sum, S2V dual, censored with the canonical. Okay. So since we have this direct sum decomposition, actually phi decomposes as the sum of two things, a beta and a gamma, right? So beta lives here and gamma lives here. Okay. So let me just say one word about what the stability condition looks like in this case. Kind of instructive. So again, so if you take that general stability condition that I just erased here from this board and see what it tells you, even in this case it's still quite complicated. You have to look at so stability has to do with filtrations of V. So I want to make this V1 Vk inside V. So this is what this kind of flag is what gives you the reduction to a parabolic subgroup. Then you need these characters, so you need some sequence of real numbers, and out of this you get some numerical condition on certain let's see, if phi satisfies a certain condition. Satisfies a certain condition with respect to this data, which is kind of the analog of up there, over here, phi preserving the subbundle. Okay, so this is again a complicated condition. So instead of trying to write that down, I'll show you a simplified condition. So, in fact, if you take this condition here, the general stability condition for pairs, and try to see what it gives you here, it also gives you something that doesn't just, it's not just a condition on subbundles, but really actually on flags, on filtrations, okay? But then, of course, you can prove that it's equivalent to just this condition on subbundles. And similarly, for this case of the symplectic group, you have a simplified stability condition. So this I worked out together with Garcia Prado and Mundet, and independently also Alexander Schmidt. So Vphi is semi-stable. I'm going to write the result for semi-stability. Okay, there's analogous results for polystability and stability. Anyway, it's semi-stable if and only if for any two-step filtration, so 0, V1, V2, V, such that phi satisfies that it lies in so I take S2, V2 plus V1 tensor V, symmetrized tensor product, tensor K plus S2 V1 annihilator plus V2 annihilator symmetrized tensor product with V U tensor K. So for any such filtration and any such phi, one has the inequality that the degree of V minus degree of V1 greater minus degree of V2 is greater than or equal to 0. Okay, okay, so there's this numerical condition, and phi here has to satisfy some strange condition that's in a way that should be thought of as an analog of just phi preserving the subbundle. So here the notation is that whenever I have a subbundle W in V, I restrict W, and the kernel of this is This is W perp, okay? And here I'm just symmetrizing because this all sits inside the symmetric product. So in fact, if you think of this for a minute, it just means that with respect to this filtration, if you choose some compatible basis, the beta bit of phi lives in this upper triangular bit, and similarly for the gamma piece. Okay, so, but it's interesting to notice here that you actually really need a two-step filtration, okay? You can't really get down to just some condition on subbundles as you might have expected naively. And the reason, of course, is, as Thomas also pointed out, that these things, they have some nonlinear nature to them, okay? So you see similar kind of phenomena, for instance, if you look at just stability for orthogonal bundles. Okay, so let me just make one remark here. So for instance, this symplectic group, real symplectic group, of course, sits inside the complex symplectic group, which sits inside the general linear group. So we can associate to some sp2nr Higgs bundle, we can associate a usual Higgs bundle of rank 2n. So if we're inside some, let me see here, to a G Higgs bundle, E phi, you can just, in an obvious way, associate an ordinary, say, Higgs vector bundle of rank n. So this is a Higgs bundle. This is a G Higgs bundle. And in many cases, like in all the cases that we've looked at, polystability and semistability of the G Higgs bundle E phi is actually equivalent to the corresponding poly or semistability for the usual Higgs bundle E phi. Okay, but it's important to notice that the actual stability condition is more subtle, and there's really no equivalence in general. So but not so for stability in general. Okay.
So how can it be then that the condition on the on the SPN guys?
Right. Yes. Good question. So it's better good to see the example. So what is in the case of SPN, for instance? You have what is this? Then E. So you have to see how, of course, you embed your symplectic group in the general linear group. So just essentially embed it inside Cn via. So we can just say what's the result. So E becomes the direct sum of V and V dual. You already see here how you get the complex symplectic group here, right? So you take the standard complex symplectic form on this. And phi, with respect to this, so the big Higgs field phi has this shape. Okay, so this makes sense. Beta here is something that goes from V dual to V, tensor K. Okay, and so it makes sense to ask for that to be a symmetric section to be a symmetric section. So you see, taking subbundles, just if you take subbundles of E, you get more stuff than just subbundles of V. Okay, so and indeed you can almost, so you can see out of a two-step filtration like that, in fact you get subbundle here and a subbundle here satisfying a certain condition. So that condition there actually means that this big phi here preserves the filtration. So if you limit yourself to considering subbundles which decompose, respecting this decomposition, the two conditions are equivalent, but you may actually have to consider subbundles here which are not so nice. So things are different. Okay, so I have 5 minutes or maybe a bit more. So let me, in the last minutes, let me give a basic very nice example following Hitchin from his original paper of 87 of SL2R, which is of course also a symplectic group. So another example here. It's maybe in a way more useful or more, yeah, it's more better in a way to think of that as SP2R. I'm going to follow Hitchin's original paper here. Okay, so what is a G-Higgs bundle? So it's a line bundle, right? It's just a rank 1. This is the special case of the symplectic there. So it's L beta gamma. So L is a line bundle. Beta is a section of L squared k. Gamma is a section of L minus 2k. And if we look at the big Higgs bundle there, it's just L sum with its dual, which is the same as the inverse, 0 beta gamma 0. Okay, let's see, what does stability tell us for this case? So when is such a thing stable? So let's just think of then the semi-stability of this big Higgs bundle, and let's see. Let's, for instance, so this has degree 0, obviously. Okay, so that means that by that the general stability condition for just rank 2 Higgs bundles, if the degree of L is strictly positive, then it's not allowed to be invariant under phi. So that means that this gamma here has to be non-zero. So stability, or even actually just semi-stability, if degree of L is strictly positive, then it can't be invariant under this big Higgs field. So that implies that gamma is non-zero. But if gamma is non-zero, then certainly the degree of L has to be less than or equal to half the degree of k. So that implies that the degree of L is less than or equal to g minus 1. And similarly for L minus 1, beta different than 0. We got L minus 1 less than or equal to g minus 1. So that's just minus the degree of L. So if we put these two things together, we get that the degree of L in absolute value has to be less than or equal to g minus 1. So we get this. So this was already, so see, this is actually also can be interpreted as a statement of representations of the fundamental group of X in SL2R, right? So if we have a flat SL2R bundle, there's a characteristic number associated to it simply by taking the degree of a reduction to the maximal compact U1, and that's of course just this degree of L. So if we think of the rho corresponding to L beta gamma, there's a certain representation. So let me like that. And there was there's an invariant which is called the Toledo invariant, which is just the degree of L. So this is called the Toledo invariant of the representation. Okay, so this is something that people who like to study representations already also will study independently of Higgs bundles. And then if you think of this as an inequality for the Toledo invariant, this is actually a very well-known inequality, which is generally known as the Milnor-Wood inequality. For, let's say, the corresponding flat bundle or the corresponding representation. Let's see some. Okay. So I guess, how much time do I have? 5 minutes? Yeah? All right. So let me just, yeah. Okay, so let's consider a particularly interesting case then. Let's consider the case when we have equality in that Milnor-Wood inequality. So let's consider the case when the degree of L, say, is equal to g minus 1. Okay, that means that that line bundle of which we have a non-zero section is a degree 0 line bundle. Okay, so that means that L minus 2k is actually the trivial bundle. So L is the square root of the canonical bundle. So some square root of the canonical bundle. So if we look at what is the moduli space of maximal SL2 Higgs bundles, it's actually very simple to say what it is. So if I have here mg minus 1 x SL2 so the bundle is given to us just by taking a square root of the canonical bundle. So let's say that we have a union over square roots of the canonical bundle of some m's, one for each of these L's. We put the g minus 1. And each of these guys here, so once we have the bundle, well, gamma is just a constant, right? Because it's a section of the trivial bundle, so it can be normalized to 1, in fact. So we can let's just say it's 1. Okay, we can normalize like that by an automorphism. So all that's left, all the freedom that's left, is the choice of beta, which is just a section of k squared, so it's a quadratic differential. So this ml g minus 1 is in fact just a space of quadratic differentials. So here's essentially beta here gets sent to ml beta 1. Okay. So that was one thing. So you may remember the Hitchin map that Norbert Hopfen also told us about. So if we look at the Hitchin map, in fact, this is the Hitchin map for SL2 just goes exactly to this space. And it is actually just taking the Higgs field 0 beta 1 0 to the determinant, which is beta. So this is really a section of the Hitchin map. Okay, so that's maybe nice to notice. So the final observation I'd like to make is that, okay, what does it mean if we take such a bundle, such a Higgs bundle, where okay, let's take the simplest possible. Okay, so let's put beta equal to 0 maybe. So beta is 0, gamma is 1. Okay, so this is in fact a stable SL2 Higgs bundle. So by the theorem of Hitchin and Simpson, there is a solution to Hitchin's equations, which we can think of as just actually unitary reduction of this to U1. So it's a unitary, so it's a emission metric on K2.5. Okay, but this, okay, if we square this, we get the holomorphic cotangent bundles, which is the dual of the tangent bundle. So we're getting a Riemannian metric on the tangent bundle. So take that Riemannian metric, we should say, yeah. Let's say G0. Okay, think of this as a Riemannian metric on the tangent bundle, and see what do Hitchin's equations actually mean for this G0. And the fact, which is a calculation, is that Hitchin's equations are equivalent to saying that the curvature of this metric G0 is equal to -4. So it's constant negative curvature. So see what we've proved now is then that our Riemann surface has a metric of constant negative curvature, which is actually compatible with a complex structure. So that means we proved the uniformization theorem. Okay. So corollary to Hitchin and Simpson's theorem is the uniformization theorem. Surface has a compatible constant curvature Riemannian metric. Okay. So inside the conformal class determined by this Riemann surface structure, there's one of negative curvature, constant negative curvature. That is right, yes. So I should certainly put that condition in. Thanks. Okay, I better stop here.